אז שלום לכולם, אני שלטיאל, אני עובד בדיקטה, ואמרו לי שהמצגת חייבת להיות באנגלית, אז אני גם ארצה באנגלית.
אתה מדבר בעברית.
אני מדבר באנגלית.
אתה רוצה באנגלית?
אני אעביר באנגלית. אני מניח שכולם כאן יכולים... אז hello everyone, my name is Shaltiel, I work at DICTA, and I'd like to present our latest model, DICTA LM 2.0, an open and powerful generative LLM dedicated for Hebrew. This project was a collaboration between DICTA, Mafat, and the IALT, the Avner Algom here, who organized this whole conference. So before we even train an LLM, you have to ask the question, why would you even want to train a Hebrew LLM? Now, I'm sure if we're living in this country, many of you know the reasons why. And many of them intersect with the reasons that we want open source LLM at all. And those are reasons like privacy. If you want to use your data, keep it internally inside your system, you can't let any data leak. If you want to fine-tune the model for your very specific task that using just a prompt doesn't cover, or simply pricing. If you don't want to pay per usage, you want to run it on your own infrastructure, you want to deal with all that, and you don't want to pay per token. And so with these reasons is why open source models came to be. And even with the open source models, they came a very long way, starting with Llama, with the Gemma, with Mistral, with Llama 2, Llama 3, but yet they all still have weak Hebrew. And the question is, why do they all have weak Hebrew? And to answer that question, I'm going to present a few of the difficulties that all these models have with supporting Hebrew properly in their models. And the first issue I'd like to discuss is the data scarcity. Recent models have been trained on sums of over 15 trillion tokens with the latest model, and yet when it comes to Hebrew is the amount of data that exists in Hebrew is a small, tiny fraction of those numbers. And the number of available data is even less. So when these models train, they need massive amounts of data in order to properly understand Hebrew, and yet they get almost no representation of the language. The second issue is the tokenization. Most modern large language models use a tokenization system that's based on a variant of BPE. BPE is a byte pair encoding where you start with the bytes of the sentence, and given a corpus, it slowly combines bytes and tokens into larger tokens using a statistical method. But the statistical method is based on the corpus you are training your tokenizer on. And if there's very little Hebrew in your corpus, then the number of tokens that you'll have representing Hebrew is going to be very small. So if we were to look at a sample sentence tokenized using GPT-4's tokenizer, you can see that every word is represented by 1 or 2 tokens. But on the flip side, if we were to put in a sentence in Hebrew, you would have approximately 1 token per letter, which introduces so many issues specifically regarding computational feasibility. When you are trying to predict a word, instead of predicting 1 token or 2 tokens, you're now going to have to predict 8. Or if you have a context window of 2,000 tokens, the number of words you can insert into that context window is very small. In addition, it's much harder for the model to understand and learn Hebrew when you have such few tokens. And finally, the third issue is that there's no evaluation. Even if there would be an open source model that came out that supported Hebrew properly, we have no way of knowing how well it supports it. The best we can do is probe it with a few questions and see if we like the responses, but there aren't any metrics available in order to properly evaluate whether these models understand logic, reason, and can properly produce fluent answers in Hebrew. So this is where we come in. We propose a solution that addresses all 3 issues. The first issue is the data. So together with Mafat, we partnered with them, and together we collected around 40 billion words of Hebrew text. Now these 40 billion words are after we did thorough cleaning, we deduplicated across all the corpora, And we resulted in this corpus of high-quality text. Now, to understand what 40 billion words is if we were to use the Mistral tokenizer, we would have 204 billion tokens from these 40 billion words. On the other hand, with GPT-4, we would only have 196 billion. But again, that is still a lot of tokens. With our latest model, which we will explain in the next few slides, we were able to get it down to 95 billion tokens representing those words. And that amount of data is already a significant leap forward in the amount of, in the quantity of text that you need in order to train a model to understand the language. So once we collected the data, we moved on to preparing our model. We started with the Mistral 7B model, which was the state-of-the-art model back when we started, and had a very permissive license, which was an Apache 2.0, and we were able to use the weights and distribute it freely so we can produce a model that we can also release with Apache 2.0 weights. And now, in order to address the tokenization issue, we extended the tokenizer of the model so that what used to be 204 billion tokens would be represented by significantly fewer tokens. So we extended the tokenizer by 1,000 tokens, which reduced by just adding those 1,000 tokens, we were able to decrease the compression rate from 5.8 tokens per word to a mere 2.76. Now, that isn't as good as English, but with a simple 1,000 tokens, we were able to decrease the compression rate by a factor greater than 2. Now, I'd like to note that why we chose 1,000 tokens and just simply adding tokens isn't a trivial task, and it requires a special training in order to get it to work. Now, all these details will be released in our technical report, but I will not delve into the details in this lecture. So once we had our model set up, we set up our training infrastructure. We decided in order to avoid catastrophic forgetting, we continued training on a mixture of Hebrew and English content, where we made sure to sample from Slim Pajama English content that matches one-to-one for the Hebrew content. So we trained on a total of 190 billion tokens, 95 billion of our Hebrew content, and 95 billion from the Slim Pajama. We trained our model on the Intel Gaudi 2, on an Intel Gaudi 2 compute cluster. And I'd like to take this opportunity to thank the Intel NLP labs in Israel for their invaluable help and their support and getting it running on the Intel Gaudi 2 cluster. So after we finished training, we decided and while we were training, we addressed the final issue of the training, and that is evaluation. I saw a great quote the other day, which says, "Evaluating LLMs is the cornerstone of building trustworthy, fair, and groundbreaking AI for all." Now, evaluating a model is the most important part of training a model. If we were to take a model, train it on Hebrew, and just release it to the world and say it was strong without providing any kind of proof as to why it was strong, we would look a little foolish, because people would be like, sure, it's strong, but how do you know? And that's why at DICTA, we insisted on building a full set of evaluations in order to properly address this issue. And when we released our model, we could provide actual metrics supporting why our model was so strong. So we performed 3 sets of evaluations. The first one is automatic evaluation, where we put in text that we could automatically evaluate the response of the model using any kind of automatic measure. The second method is using human evaluation, where we presented the results of our model to a human and had him actually grade it himself in order to provide some form of human subjective grading. And finally, we use an AI evaluation where we produced results from a model and had an AI system automatically evaluate how good the responses are from our model. So we'll start with the automatic evaluation. The first data set we took is for Hebrew question and answering. We took the HEC data set and we converted the test set into a format that a base model learns how to respond to. And then we graded it using the TLNLS score, which was introduced in the HEC data set. This measure helped us evaluate how well the model understood questions and its information retrieval ability. The second data set we used is sentiment analysis. We used the Hebrew sentiment data set that was released by the National Program for Natural Language Processing in Israel. And we had a linguist actually pick out 3,000 examples, 1,000 from each of the categories, in order to choose the least ambiguous cases in order to provide with a more concrete measure. And that way, we were able to test how well the model was able to pick up on hidden cues in the sentence in order to understand whether a sentence was actually positive, negative, whether it understands sarcasm, and so on. The third data set we use is Winograd, which we use the translation of the Winograd Schema Challenge to Hebrew, which was translated by Dr. Vered Schwartz. And this data set contains a bunch of sentences with contextual ambiguity that the model has to use logic and world knowledge in order to figure out, in order to disambiguate the sentence. And so this was a very important test that really tested the model's understanding of delicate Hebrew. And finally, we tested the model on translation, where we translated the model between, we took 1,000 sentences from the New Labs TED Talks data set and had the model translate them from Hebrew to English and then in the other direction. And we measured the quality of the translation using the standard machine translation measure, which is the BLUE score. And we compiled all these data sets together and produced an open LLM Hebrew leaderboard. This is the first leaderboard of its kind that actually can measure the quality of and the reasoning and the abilities of a generative large language model on Hebrew. Now, this leaderboard is available to everyone. There's a QR code for anyone who wants access to it. And it's available online, and anyone can just simply log in and submit a model. And you can fine-tune your own model, you can train your own, and they'll all just go up automatically onto the leaderboard, automatically graded. This was very important for us as a leap forward in order to encourage more development in Hebrew. Now, as you can see, the DICTA model produces results that are supreme to all the other models on the list. The second set of evaluation we used was human evaluation, where we used the translation preference question, where we translated 1,000 sentences from English to Hebrew. We translated them both using DICTA LM 2.0 and Google Translate. And then we anonymized the translations and presented them to a human in order to simply pick which translation he thought was better, without any other knowledge of which models to avoid any bias. You can see here that after tagging 1,000 sentences, over 74% of the time, he preferred the translation that our model produced over Google Translate, which is a huge step forwards in our opinion, which also releases a proper translation tool to the hands of the public. The last measure we use is AI evaluation. We use a summarization task. This task is evaluated on instruct models, not on base models. And we tested, because in order for the model to properly understand the task, we provided it with lots of instructions. And we took 75 documents that had human summaries as well. And we compared the summaries using different models, where we generated a summary using various models. And then we used GPT-4 to evaluate the model on 4 different measures. We evaluated on relevance, coherence, consistency, and fluency. And as can be seen, we don't reach the level of the closed models of Claude 3, GPT-4, which have resources beyond what we can get. But we do put up a fight, and for anyone who can't use these closed models, we are providing a strong base, a strong alternative for anyone who wants to use it. So what's next on our agenda is starting with encouraging community engagement. We would like to encourage the community to train more models, to use the model, to really push forward anyone who needs to use this. We released the model for easy deployment in all these in various infrastructures at LM Studio, VLLM, in Replicate, and we are working with other companies in order to make it even easier to deploy using other infrastructures. And we are constantly using adding more evaluation metrics. Just last week, we added the SNLI the SNLI metric, and we are constantly adding more to the leaderboard in order to have the leaderboard present more fair and accurate representations of the various models on various reasoning tasks. We are also going to fine-tune the model for custom uses in order to release it to more specific uses. And finally, we're going to train bigger and better models to release to the public. Thank you.